Hi everybody, welcome to the revision series. In the previous video, we covered these key topics from unit number 1. And in today's video, we are stepping it up. We will be revising the number system, binary, octal, decimal and hexadecimal. Then we will go through conversion methods, switching between these systems step by step, followed by different encoding schemes, how text and data are converted into formats computer understand. By the end of this video, you will have a clear, strong grasp of these topics, exactly what expected in your exam. So grab your copies and let's get started. Here is the first topic, that is number system. We are already familiar with two number system, international and Indian. Our Indian number system uses decimal number system, but apart from that we have three other number system, binary, octal and hexadecimal. We understood different types of number system, but what is it exactly? So it's a method of expressing numeric values. Let's discuss the first one, that is decimal number system. It uses digits from 0 to 9. So there are total 10 digits. That's why the base of decimal number system is 10. Base is nothing but the number of digits used in that particular number system. The second number system is binary number system. Here we use digits 0 and 1. So total digits are 2. That's why the base of binary number system is 2. It means all the numbers of binary system will be consist of only zeros and ones. And this is the language computer understand. That is nothing but binary language, right? Moving to the third one, it is octal number system. It has digits from 0 to 7. So total digits are nothing but 8. That's why the base is 8. To form a number in octal number system, we cannot use other digits except 0 to 7. The fourth number system is hexadecimal number system. From the name itself, we can guess how many digits we will have. Decimal is nothing but 10 and hex is nothing but 6. It means there are total 16 digits. Digits will be from 0 to 9. After that, the remaining 6 digits will be represented from A through F. Look at this table. Digits from 10 to 15 as A through F. Now it is clear to you why the base is 16 of hexadecimal number system. Alright, we understood all four types of number system. In decimal number system, we use digits from 0 to 9. There are total 10 digits, that's why the base is 10. In binary number system, we use only 2 digits, 0 and 1. So total digits are 2, that's why base is 2. Whereas octal number system uses digits from 0 to 7, total digits are 8. And in case of hexadecimal number system, we use digits from 0 to 9. After that, we use letters A through F. Total digits are 16. Hope it is clear to you now. If you get any theory question on it, you can write it easily. Let's proceed. The next topic is number conversion. We have to convert numbers from one number system to another. There are total 10 conversions in your syllabus, which are divided into 3 sets. The first set is from decimal set. It means we are converting the number from decimal number system to binary, to octal or to hexadecimal. Here is the next set. In this we are going to convert number from other number system to decimal, like binary to decimal, octal to decimal and hexadecimal to decimal. In this way total 6 conversions are covered. What are the remaining 4? In this set we are going to convert to and from binary. But decimal to binary is covered and binary to decimal is also covered. So these 2 conversions will not be a part of this set. So the conversions are octal to binary and hexadecimal to binary and the reverse of it, binary to octal and binary to hexadecimal. Hope you got the overall idea of the number conversion. Now the question will be, but how to do it? Don't worry, that we will be discussing in a while step by step. Let's check out the first set, which is from decimal. From decimal to binary, from decimal to octal, from decimal to hexadecimal. So whenever you see the question of conversion, first try to fit that question in one of the set. Then the conversion will be easy. Alright, how the conversion will be? Suppose if it is a decimal to binary. What we need to do? We will be dividing the given number repeatedly by 2 and then we have to note down the remainders from bottom to top. In the same way, if the conversion is from decimal to octal, the base of octal number system is 8, so we will be repeatedly dividing by 8. Now you got to know how to convert decimal to hexadecimal. We will be taking the base of hexadecimal number system, that is nothing but 16. We will keep on dividing by 16. Note down the remainder from bottom to top. So simple, right? But you know, theory will not work out here. We need to practice some conversions. So let's do it. Here is the first one, decimal to binary. We know that if you want to convert it, we have to repeatedly keep on dividing the number by 2. Here is the given number, that is 11. 2 5s are 10, remainder is 1. Let's continue. 2 2s are 4, remainder is 1. 2 1s are 2, remainder is 0. We will keep on dividing until we get 0. Here is 1. So let's divide this number by 2 once again. 2 zeros are 0. The remainder is 1. Look at the last digit. We finally got 0. Now we will stop this process. It's time to note down the remainder from bottom to top. Final answer will be 1011. Don't forget to write this final answer because on the steps you will have the marks. Hope you understood this explanation. Here is one more example for practice and there is the answer too for cross-checking. Feel free to practice more conversions. Now we are moving ahead to the second conversion of the first set, that is decimal to octal. Let's take the base of octal number system, that is 8. It means we will keep on dividing the given number by 8 until we get 0. Let's take one example and here is the same process. 8 15s are 120, the remainder is 3. 8 1s are 8, the remainder is 7. Look at the digit, it is 1. Let's divide it one more time. 8 zeros are 0, the remainder will be 1. We finally got 0. Let's stop the process. Time to note down the remainder from bottom to top. It is 173. In this way, we got the final answer. These conversions are very easy, isn't it? Let me know in the comments. For this, only you should know the basic mathematical calculations and tables. For your practice, here is one more example along with its answer. Moving ahead to the third conversion, decimal to hexadecimal. The base of hexadecimal is 16, so we will keep on dividing by 16. The given number is 423. I know you can do these calculations. Here are the remainders. In this conversion, please note that if you get any number from 10 to 15, you need to replace it with A through F. Here the remainder was 10. Then we replaced it with A. Here is one more number for practice. I will highly recommend you to solve this. Hey, what if we have fractional number? For the non-fractional part, we will follow the same process. Here we are converting decimal to binary number system. So we are repeatedly dividing by 2, noting down the remainder from bottom to top. But what about this fractional part? For that we will be following this process. We have to multiply that fractional part by 2. For non-fractional part we need to divide, but for fractional part we need to multiply. Here we note down the remainder, but here what we need to do? Let's check out. This is the fractional part, 0.825 multiplied by 2. Here we will be noting down the non-fractional part of the resultant number. Then after taking out that non-fractional part, keep on multiplying the fractional part again with 2. Repeat this process. For this number, here is the non-fractional part. In the next step, we got 0. We did one more step. In this step, we got 1. Look at this number. Now it is 0. It is of no use continuing further. One more point. We will be writing this non-fractional part from top to bottom. Just reverse to the non-fractional part. That's why we got 1101. Here is the answer for the non-fractional part and here is the answer for the fractional part. Now question may arise in your mind, what if we don't get 0? Because always you will not get this term. In that case also you will be doing only 4 steps, that is enough. Because it is indefinite, we cannot keep on doing this calculation. So 4 multiplications are more than sufficient. Hope you got the overall idea. Same process will be followed for the conversions from decimal to octal and decimal to hexadecimal. You know that what will be the change? We will be multiplying by the base of that number system. I hope the set 1 is clear to you now. Moving ahead to the set 2. In this we are converting binary to decimal, octal to decimal and hexadecimal to decimal. How to do these conversions? Each digit of the given number will be multiplied with its base positional weight. And then we have to add them all. What is this base positional weight? Every digit of that number system has positional weight. Let's take example of a binary number system. Each digit from LSB to MSB will get multiplied with its positional weight. Binary number system has base 2, that's why we will take 2 and the power will be starting from 0. In this way it will keep on increasing from right to left. And if it is a fractional number, we will start the power from -1. That we will start from left to right. Same concept will be followed for other two number system, octal and hexadecimal. I know without practicing any example, it is difficult to understand. Then let's check out one example. This binary number we have to convert to decimal because we are in the set 2 decimal. Here is the number 100 and here is the positional value 2 to the power 0, 2 to the power 1 and 2 to the power 2. Multiply each digit with its positional value. If it is a 0, 0 multiplied by any number will be 0. So no need to calculate this. Directly we got 1 into 2 to the power 2. It means 4. So this 100 is a binary equivalent of number 4. Hope you understood this. Let's check out for the fractional part now itself. We will be taking negative power, but that too left to right. The number is 0, 1 and the positional weight will be 2 to the power -1, 2 to the power -2. Don't forget to write these steps because we have marks on the steps. We will not calculate for 0 because any number multiplied with 0 will be 0. The remaining term is 1 into 2 to the power -2. How to calculate the negative power? First we need to make it positive. How to make it positive? By writing it to the denominator. Now you can solve this. It is 1 divided by 4. It will be 0.25. Look at the answer. We got it. Then we can add them. This is the non-fractional and this is the fractional part. The final answer is this. Don't forget to write the final answer. You can solve this together also if you feel it easy. In this way, we understood how to convert binary to decimal. It's time for octal to decimal. Same process we will be following. Here is the given number and here are its positional weight. Multiply it and solve it. I trust you. You can do it yourself. Pause the video and finally you can cross-check your answer. If you want one more example for practice, here it is. So by now you are expert in converting binary to decimal as well as octal to decimal. One is remaining, that is hexadecimal to decimal. The process will be same. So here is the given number which we need to convert. Here are the positional weights. Keep this table in mind that you need to replace 10 to 15 with A through F. And here is the calculation. A is replaced with 10 and F got replaced with 15. Multiplication and addition you can do it, I know. Here is one more example with the fractional part. Pause the video and try it yourself. Let's go back and revise. This is the first set and this is the second set. Take a screenshot of this screen. I would suggest to take the screenshot in your eyes. So whenever you see that conversion question, this screen should flash in your mind. It's time to move ahead to the third set. This set I can name as to and from binary, but note down Already we have discussed binary to decimal and decimal to binary. So these two conversions are not part of this set. Only we will be doing binary to octal, binary to hexadecimal and reverse of it. But how we are converting it? What is this direct conversion means? Let's check out. We are converting octal to binary. How to do this direct conversion? We have to substitute these numbers with the 3 bits binary number. 2 got replaced with 3 bits binary number, 7 got replaced, even 4 got replaced. But how to calculate this and how we got it directly? It is also so simple. Let's understand. We know this positional weight of the binary number system. It starts with 2 to the power 0, then 2 to the power 1 and 2 to the power 2. Why we are taking only 3 bits? Because 3 bits are sufficient to represent octal number system. In octal number system, there are total 8 bits and 2 to the power 3, it means 8. So 3 bits are sufficient. Now how to get this binary equivalent? Look at this, 2 to the power 0 means 1. You know that, right? Any number power 0 is equals to 1. 2 to the power 1 will be 2 and 2 to the power 2 will be 4. Now let's start with the first digit of the octal number system, 0. For 0, we will be writing all 3 bits as 0. Let's move ahead to the next digit, 1. Look at only this column now. How you will get 1? By placing 1 in the column where you have 1. Other bits will be 0. You got the equivalent of 1. Now how to get the equivalent of 2? In which column you have to write 1 bit for that column, other bits will be 0. Hope you are getting my point. Let's move ahead to the next digit, 3. How you can get 3? By adding 2 and 1. So write the bit in that equivalent column as 1, remaining bit will be 0. In this way you got the binary equivalent of 3. How you will get 4? You have 4, right? So write that bit 1, remaining bits will be 0. Now you do yourself. How you will get 5, how you will get 6, how you will get 7. 5 means 4 plus 1. So here it is. 6 means 4 plus 2. So we are writing the bits as 1 in that column. 7 means 4 plus 2 plus 1. All the bits are 1. In this way we get the binary equivalent. I would suggest to write this table first time to get the practice. Later on you can do it directly. So write the binary equivalent for 2, 7 and 4. Here is the final answer. Here is one question for practice. Give it a try. We just understood how to do octal to binary. Then why not understand the reverse of it? Binary to octal. For that, first of all we need to make a group of 3 bits starting from LSB. Means what? Starting from this side, right to left. So here are the 3 groups. We know that binary numbers also has its own positional weight. So write down it. 2 to the power 0, 2 to the power 1, 2 to the power 2. In this way write down the positional weight for the remaining set. Then we have already understood what we do next. We multiply this positional weight with each digit and we sum it. But here is the catch, no need to do for the zeros. Ultimately the term will be 0. What's remaining? 1 into 2 to the power 1. 1 into 2 to the power 1 means 2. Calculate in the same way. We got 472. Here is the answer. Hope you could recall. We started with this in the previous conversion. 472 got converted to this number. Here is that question. So for all these 10 conversions, you can cross check by doing the reverse conversions. We have done lot of exercise to the brain, right? If you wish to take a break, pause the video. But there are only 2 conversions are left. So stay consistent. Here is the conversion from hexadecimal to binary. Here is the given number. The same process we will be following which we followed for octal to binary. We directly place the binary equivalent for that octal number, but we place 3 bits binary number. Why? We understood already. But in case of hexadecimal number system, we cannot take 3 bits because in hexadecimal number system we have total 16 digits which we cannot represent with 3 bits. For that we need 4 bits. Now how to calculate 4 bits binary equivalent? Look at this answer. 2 got replaced with 4 bits binary number, then F, then 9. Don't worry, same process we will be following here. One change only we will be doing, that we will be adding one more positional weight. For octal we took only 3 bits. Here we are adding one more, 2 to the power 3. It will be 8. Now the rest is just addition. So 0 to 7 conversions we understood. How you will get 8? We know that we have already one column 8. So place one bit there, remaining bits will be 0. In the same way proceed for 9, 10, 11, 12, 13, 14. 10 to 15 we will be considering as A through F. Now you can place the value. 2 is this, F is this and 9 is this. Here is the final answer. To understand this conversion is very important and it is very easy. Now it's time to do the reverse of it. Let's check out. Here also we will be following the same process as binary to octal. But the difference will be, it will be a group of 4 bits. Look at this. If you don't have the sufficient bits, what you will do? You will add zeros on the left hand side. In this way we got these 3 groups. Now place the positional height, multiply it and add it. Wherever there is 0, no need to calculate. After calculation you may get these numbers. You know we don't have 10 in hexadecimal, replace it with A and 11 will get replaced with B. So here is the final number. With that conversion we are done with all 10 conversions. Hope you understood and it is helpful to you. The next topic is binary addition. For that you need to keep these 5 rules in mind. If you are adding 2 zeros you will get 0. 0 plus 1 will be 1. In the same way 1 plus 0 will be 1. What if you need to add 1 plus 1? You will be writing 0 as answer and there will be carry 1. And here is the fifth rule. If you are adding 1 plus 1 plus 1, you will be writing 1 here and the carry will be 1. With that you can add any number. Look at this number, 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 0 will be 1, 1 plus 1 will be 0 and carry 1. Now this is the case of fifth rule, 1 plus 1 plus 1. Now there is no other bits, so we will be writing both the bits here itself. The answer is 1 and the carry 1. Finally we are at the last topic, it is encoding schemes. We have different letters and symbols on the keyboard. But how this computer will understand? For that it uses encoding schemes. These numbers and letters will get converted to some integer value. And this integer value is fixed. There are 3 different encoding schemes. The first one is ASCII, the second one is ISCII and the third one is Unicode. What is this ASCII? Keep this full form in mind. American Standard Code for Information Interchange. This is the oldest encoding system. It has integers from 0 to 127. It means total 128 letters and symbols can be represented using ASCII code. But that was not sufficient. You can note down it is an American standard. It means it is specially for English. Then what about our Indian language? Our Indian culture has many languages. For that we have this Indian Scripts Code for Information Interchange. Here there are total 256 possible code groups which are used for representing our Indian languages. Apart from that there is a Unicode encoding scheme. Nowadays it is used because it represents majority of the known languages. Look at this number. It has 3 types, UTF-8. The next one is UTF-16 and the last one is UTF-32. So that was all about encoding schemes. Alright then, fantastic job revising those important concepts. You are getting stronger and more prepared each time. If this video helped, hit the like button, subscribe for more and ring the bell so you don't miss the next one. In the next video, we will be revising Boolean logic from the same unit. So until then, keep learning, stay motivated. I will see you in the next video.